So, we have seen in our last lecture, for a given linear transformation from a vector space V into vector space W, it gives a, it introduce a another linear transformation T star from W star to V star. In fact, this is a unique linear, I mean for each linear transformation T, it introduces a unique linear transformation T star from W star to V star, such that T t of G equal to G into T basically, I mean to say T t operating on G, G belongs to W star, T t G of any vector alpha belongs to capital V is equal to G of T of alpha, please. I mean to say this T t G is a basically linear functional on V star. So, for a given linear transform T, we have another linear transform T t is basically linear transform from W star to V star, please. As in the case of a linear transform T from space V to V W, we know when V is a finite dimensional vector space, then we know the rank of T plus nullity of T equal to dimension of V. Question is whether similar type of results holds good for the case of this transpose of linear transformations T, that is T t. I mean to say, if the rank of T is known to us, what way this will be related to the rank of T transpose? How the range space of T transpose, how the null space of T transpose are related by the null space or range space of T. So, these things we have to study, please. Here I am claiming like this, say let V and W be vector spaces over the field capital F and T be a linear transformation from V into W. Then the null space of T transpose is the annihilator of the range space of T. If range space of T is equal to, if you denote as RT, then RT naught is basically the null space of TT. So, this is true irrespective of V and W whether finite dimensional or infinite dimensional. It is true for both the cases. If V and W both are finite dimensional, in that case rank of T equal to rank of T transpose, and the range space of T transpose is the basically annihilator of the null space of T, please. I mean range space of T transpose is, if you consider capital N is the null space of T, then range space of T equal to N naught, that is the annihilator of the null space of the N, null space of the transformation T. So, let us give a proof of these results, very interesting results, so that later on we will correlate this concept with the matrix, please. Although we have already used the concept of transpose of a matrix, all these things we have already used, but the relation between the transpose of the matrix and linear transformation is not studied so far. So, that we are going to highlight, please. Anyhow, I will come to that part later on, but before that let me correlate the range space of transpose T transpose and null space of T transpose with the some relation with the range space of T and null space of T, please. First claim is that the null space of T transpose is the annihilator of the range of T. Okay. Let NTT denote null space of T transpose. We know T transpose is basically mapped from W star to V star. For any G belongs to NT transpose T, we have from the definition T transpose of G equal to GT, okay, that is basically 0 functional, that is 0 functional. This implies that TTG operating on any alpha is equal to G of T of alpha equal to 0 for all alpha belongs to V. This implies G belongs to, see, since G is annihilating all elements in the range space of T, so G belongs to RT naught, where RT denote range of T and RT naught is the annihilator of RT. I said all the linear functionals which annihilate RT is called RT naught. So, G belongs to RT naught, please. So, this implies that NTT, the null space of T transpose is a subspace, a subset of RT naught, please. Again, if G belongs to RT naught, this implies G of T of V equal to 0. I mean to say, I can say that is G of T of alpha equal to 0 for all alpha belongs to V. So, this implies G is basically belongs to null space of TT, because G annihilating entire range space, I mean T all alpha, please. So, G belongs to this one. So, this so we have RT naught is a subset of NTT. So, 1 and 2 implies RT naught equal to NTT. Okay. So, null space of T transpose equal to the annihilator of the range space of T, please. This is the first one. We have for finite dimensional vector space V and W. For finite dimensional vector space V and W, we have dimension of RT plus dimension of RT naught equal to dimension of your W. So, if dimension of W is M and dimension of V is N, then dimension of RT naught is equal to dimension of W minus dimension of RT, which is equal to M minus dimension of RT. Let rank of T, let rank of T be smaller. So, this implies dimension of range space of T is equal to smaller. So, this implies dimension of T naught equal to M minus R, because that is the dimension of the range space. So, we have dimension of T naught equal to this one, which is equal to then dimension of null space of T, because we have seen that null space of T, I mean transpose of T is basically annihilator of the range space of T. So, that is why dimension of NTT is equal to your M minus R. So, if dimension of NTT is equal to M minus R, then we have from rank nullity theorem, we have dimension of NTT plus rank of TT equal to dimension of W star, which is equal to M. So, this implies rank of TT is equal to M minus R, which is equal to R, that is equal to rank of T, please. So, rank of T transpose and rank of T are same. This is very fundamental results and classical one also. So, we see the rank of linear transform T and its transpose are same place, if these are defined over the finite dimensional vector spaces, please. Now, we want to show other results, that is the range of T transpose is the annihilator of the null space of T. Let N denote null space of T. Claim N naught equal to RTT, that range space of transpose T transpose is basically annihilator of T, please. We have for any f belongs to RTT, please, range of T transpose, there exists G belongs to W star such that f equal to GT, that is T transpose of G, f will be equal to T transpose of G, please. So, this implies for alpha belongs to N, if alpha equal to 0, because f of alpha equal to G of T alpha, which is equal to T alpha equal to 0, because alpha is null space of T. So, it is 0, please. So, this implies f belongs to your N naught, I mean f annihilate your N. So, any element f belongs to range space of T transpose annihilate N, please. So, f belong to this one. So, this implies RT transpose is a subspace of N naught. We know the dimension of range space of T transpose equal to small r, that is dimension of range space of T please. Now, let me see the what is the dimension of n naught equal to what? We have dimension of n equal to n minus dimension of R t is equal to n minus R please. So, dimension of n equal to n minus R. So, dimension of n plus dimension of n naught equal to dimension of V equal to n. So, this implies your dimension of n naught will be equal to n minus r which is equal to r. So, that is equal to dimension of range space of T transpose. Since both are having same dimension and range space of T is a subspace of n naught. So, this implies range space of T transpose is exactly equal to n naught. So, range space of T transpose equal to the annihilator of the null space of linear transpose T. Okay. So, this a nice relation we have established. Now, let us go to the matrix representations of the transpose of the linear transformation please. So, for this let us write down these results. When I am talking about the matrix representations, certainly I am saying that V and W are both finite dimensional vector spaces please. So, let V and W be finite dimensional vector spaces over a field say capital F. Let B equal to, I mean this italic B, alpha 1, alpha 2, alpha n and B prime equal to beta 1, beta 2, beta m be order bases of V and W respectively. Let B star equal to B1 F1, F2, Fn and B prime star equal to G1, G2, Gm be the dual for B and B prime respectively. I mean they are the basis for the V star and W star respectively. Let T be a linear transformation, from V into W with matrix representation of T with respect to order basis B and B prime is equal to say A. So, A is a m cross n matrix please and matrix representation of T transpose with respect to order basis B prime star and B star is equal to say normal B please. So, this is a n cross n matrix, this is n cross n matrix please. Then A I j is equal to B j I for 1 less than or equal to I less than or equal to m and 1 less than or equal to j less than or equal to n. So, if B stands for the transpose matrix, I mean matrix representation of the transpose linear transform of T, and if A denote the matrix representation of T, then A and B are related like this, basically A equal to transpose of B or B equal to transpose of A. So, let us give the proof please. It is given T map from V to W and matrix representation of T with respect to B and B prime equal to A, the M cross n matrix over F, and matrix representation of T transpose B prime star is equal to B, the n cross M matrix over F. So, T of alpha j, if we consider the matrix representation of T alpha j with respect to order basis B prime, that is basically your jth column, that is jth column of matrix A, that is T of alpha j is equal to, one can write down sigma A k j and your beta k equal to 1 to m, and T transpose G j is equal to, in the same manner I can write down B k j and B k j and your F k, your k equal to 1 to n please. This is the given information to us please, according to this, that matrix representation of T transpose with respect to B prime star and B star is a B matrix means like this thing please. Now, if I see T transpose of G j, if I consider say this one and suppose operating on alpha I, this is equal to how much? This is equal to, you know, G j of T of alpha I. For sake of simplicity, I can make it is here I and this is j, so it will be nice, or I can say T T of G I and alpha j, this will be equal to G I and T of alpha j. Just for sake of simplicity, I have taken this one please. Okay. So, this is equal to this quantity. So, this implies that G I operating on T alpha j is equal to, we have sigma A k j and beta k equal to 1 to n and I equal to 1 to m. So, we have T T j I operating on alpha j equal to like this thing. So, according to the definition, this is equal to, I can write down, one can A k j and G I beta k, your k equal to 1 to n, and this is equal to G I beta k is equal to delta I k. So, this is equal to your A I j, because G I beta k equal to delta I k. this implies like this thing. So, T T G I alpha j equal to A I j. At the same time, T T G I equal to, according to our given conditions, T T G I equal to sigma B K I, sigma B K I and F k, k equal to 1 to n. So, this implies, if I given this is the information given, this is 1, this is 2. So, from 2 we have like this thing. So, T T G I when it is operating on alpha j, that will be called to again sigma B K I F k, k equal to 1 to n operating on alpha j. So, this will be equal to again sigma B K I and F k alpha j. So, this is equal to, when k equal to j, then only I will have 1, otherwise 0. So, this is equal to B j I, this is your, sorry, this is 3 and this is suppose 4. So, 3 and 4 implies that A I j equal to B j I for 1 less than or equal to j less than or equal to n and 1 less than or equal to I less than or equal to m. So, B is the transpose of matrix A. So, that is all the proof. So, we see that the matrix representation of T transpose is basically transpose of the given matrix, I mean matrix representation of the linear transformation T. So, we see that the image of T transpose G I when it is operating on alpha j. So, in this case it is basically B j I, that is the jth entry of the matrix B, whereas previously we have already obtained the image of alpha j under T T G I is basically the ijth entry of the matrix A, that is A I j. So, since both are same scalar quantity, so certainly A I j has to be equal to B j I. So, this implies matrix representation of the transpose of transformation T is basically the transpose of the matrix representation of the linear transformation T. So, B is the transpose of A. I hope this is clear to all of you, and you can utilize this concept for proving some other nice results in the linear transformation please. Thank you.